In this video, we'll begin our discussion of section 7.4. This will be taking derivatives of the transform, the Laplace transform. So we're going to prove it right here in this one line I typed out to kind of save us some space and some time. So we are taking the Laplace, right? We take that first, and then we take the derivative with respect to s. Okay, so what we're going to do is start working on this definition. So we pulled the definition out of that. And then what they've done now, and the next step is that they have taken the derivative with respect to s and they brought it inside the integral. But since t is also a variable inside the integral, it changes to that partial. So that's why it changed the d's to those. So that's a partial now. So they take the partial with respect to s, all right? And we get a negative that comes out, and then we also get a t. So it's a negative t because if I do use a derivative, I do the chain rule, I get e to the negative st there, but I also get a t right there. And that's and the negative. Those two go together. That's from the derivative of negative st. Right? The negative comes out. I then have t, and I can put it right ft, and that goes inside there. And that's what we get, our negative Laplace of that. So the derivative is equal. So let me clear all that out. I know that this side, this side is equal to this side. So I could just divide by negative, and I get that the Laplace of t f of t is negative the derivative. If we were to keep going, we could do the second derivative and the third derivative, and we'll just leave that to an exercise if you'd like to try the second and the third and start looking for that pattern. We actually fall into this definition. We get -1 to the nth, so whatever t to the nth power is, will be -1 to the nth plus negative, and then it'll be the nth derivative of our Laplace of just the function. All right, so we're going to do two problems here. So I'm going to put a line down the middle of this page. We're going to do cosine as well. We're going to need it a little later. All right, so let's use this definition to come up with a Laplace for this. Okay, so this definition says it's -1 to the nth. The nth is the power there. So it's to the first, and then times the first derivative with respect to s, and then it's going to be the Laplace of sine k t. That was our f in this case. All right, so that gets me a negative d ds. Okay, and then the Laplace of that, so I'm going to do parentheses of sine is going to be s squared plus k squared over, and then k is on the top. All right, we could bring that negative in if we wanted to. I think I am going to. So let's go ahead and I'm going to take that out and throw it in there. All right, we have to take the derivative. I'm going to rewrite this thing. Guess I could have put the negative in here. Negative k times s squared plus k squared to the -1. I'd rather do this since the only variable is s, and I only have one of those. So I think the chain rule would be a little easier here. So if I take the derivative, I don't need that anymore. -1 comes down. I get k times s squared plus k squared to the -2, and then it's going to be times 2s. It's the chain rule. All right, so what that gets me then is that 2ks, and then the other thing goes to the bottom. So there's our sine definition. All right, we're also going to do cosine. I know it's not here, but go ahead and write it in. So the Laplace of t cosine kt. It's going to follow. I'm going to write the definition down. And then the Laplace of just the cosine. It's going to be a little different, so looks similar, but things change. Okay, so that gets me negative d ds. And then the Laplace of cosine kt is going to be s over s squared plus k squared. Okay, I think I'm still going to, no, let's use the quotient rule. So I'm going to get negative, and then low d high, which is just a 1, minus high d low, which is 2s, all over s squared plus k squared squared. Okay, so that's my derivative, right? I'm going to leave that negative out there for a moment. And I'm going to get on top, I'm going to get, that's a negative 2s squared. So I'm going to get a k squared minus s squared. And then s squared plus k squared squared. And then that negative is just going to flip the subtraction. So s squared minus k squared over s squared plus k squared squared. All right, so there's our cosine. All right, we're going to potentially use these moving forward. So practicing the definition there. And then to go further, I'm just going to change the ends and do more derivatives. Most of the time with these, the t sign is just pretty popular is the wrong word, but it comes up quite a bit. Okay, so we have a few more that we're going to do in this video. So let's make it just a little more complicated. Okay, it's going to be treated a bit the same way. All right, so the Laplace of, remember Laplace, like um, plus addition remains the same over, Laplace remains the same over addition, meaning the Laplace over a sum is the same thing of the Laplace of each one and then add them together. All right, so that means I could take the Laplace of this and then the Laplace of that. That's what I'm getting at. All right, so sine of kt is going to be k over sine squared plus k squared, and then plus, okay, and then this is just kind of what we just did. All right, we have a k there, so we'll multiply the k through, so I get s squared, and it was s squared minus k squared, like there on top. So it's going to be s squared times k minus k cubed over s squared plus k squared squared. All right, so that's what happened, why everything gained a k was right there, right? All right, so I'm going to get a common denominator here, which is going to be s squared plus k squared squared. And then I needed to multiply the first fraction by another s squared plus k squared. Right. And then I'm actually going to factor, I know we distributed the k, but I'm going to factor it back out. I do that often where I'll move forward and then realize I didn't need to do that. Okay. Now, if I add everything together, the reason I left it like that is because it's a little easier to see what things are going to stay and what things are going to cancel. The s's are both plus, but the k's are both minus, and we're multiplying both by k's. So you can see that we're going to get on top, we're just going to get a 2k s squared over s squared plus k squared squared. All right. These show up often, so we'll go ahead and do that. You don't have to memorize them. You'll get a table, right? But I want to make sure you understand where these are coming from. It's not just magic. All right, we'll do another one that's pretty comes up often. Right, same thing. It's almost, I think we could actually, I can be lazy here. I'm gonna go ahead and copy and paste this. The only thing that changes really here is now that I have a minus in between. So we have a minus there. Okay. So what that does for us though, is it's going to flip the signs on the back half. So this is just plus, and then we have plus k cubed minus s squared k. So you could flip it if you'd like. Right? I need another common denominator. All right, the common denominator is going to be s squared plus k squared squared. This will be k times s squared plus k squared. That first fraction needed that. Minus s squared k. And I think it makes sense to take the k out again here. Minus k times s squared plus squared. And then to make that work, though, that was going to need to be a k squared, s squared minus k squared, right? Because if this distributes negative k times negative k squared, I need the positive k cubed, right? Okay, you can see now that's going to keep the same denominator. So I'll do that. Squared. And then you can see where the positive and negatives work out this time. I'm going to have a k squared s squared, and then a minus one. So those are the ones going away. So I'm going to have a k cubed plus k cubed. So it's a 2k cubed. All right. Let me double check that real quick. It is a k cubed. Cool. It felt weird, but it is right. All right. Okay, we are going to solve a problem that requires a bit of this, and then we'll end the videos there. So just algebra again, always, right? Okay, so solving this second order derivative with a couple initial conditions. So solving an IVP, it's going to be starting off, it will be the derivative, the Laplace of both sides. Okay, so same rules that we've had. Second derivative is s squared times y of s minus f times y of 0 minus y prime of 0. And then don't forget we have another ys from the y in the back. That's where I mess up, is I end up forgetting that. And then on this side, I get a 1 over s squared plus 1. All right, let's go ahead and put it in everything. Okay, got that. And then y of 0 is 1, so I'm going to have a minus s. Minus y prime, that's a negative 1, so I'm going to have a plus 1 plus y of s equal to nothing changes. All right, so I'm going to do a couple things here. You can see that y of s is in this term and that term. So we're going to get y of s squared plus 1. And then I'm going to go ahead, this side's still going to have this fraction, but it also, I'm going to add s and minus 1 from the other side. All right, we're going to divide everything by s squared plus 1. So we'll get y of s equals, okay, we're going to get a 1 over s squared plus 1 squared. And then we're going to get an s. We're going to go ahead and break it all the way down like this. S over s squared plus 1. And then plus a negative 1 over s squared plus 1. So I didn't just divide s minus 1. All right, the reason I did this is now I can actually go ahead and just take each inverse Laplace. It's already set up for us, so we can actually do it here. So let's talk about how this is done. Okay, so we're gonna have y of t. Let's skip the first one for a moment because the other ones are a little quicker. You can see that I have s squared plus 1 over s. That's just a cosine of t. It might look weird because of the parentheses, but if I take it off, you might be able to see it a little better. Let me just rewrite that. Didn't mean to delete everything. I don't know if that's much better than what I had. I'm going to go ahead and make my eraser a little smaller, so I'll quit doing that. Okay, and then I got minus because I'm going to take the negative, and you can see here that's that same thing, but I have a 1, not an s, and 1 is the 1 squared on bottom, so I'm going to have a sine of t, right? And then I'm going to do some manipulation to this one, so I'm going to do an inverse Laplace. Hopefully you got some room there, sorry, and we might not need all that. I'm going to put a little fraction there because I know I'm going to need to counter some stuff out. Okay, this is, if I put an s squared plus 1 squared on bottom, nothing changes there. But I'm going to put, because I have a 1 on top, I'm going to put a 2 here, and then I'm going to put a 1 squared. I know that's kind of silly, but I really want to emphasize why I put that. And not squared, but cubed, sorry. So I get 1 over 2. There we go. You probably, hopefully you had room there. So the twos cancel. I don't really need to counter 1 to the third power. But the reason I did that is that you can see if we go back to that last page, that I'm going to get the 1/2. Let's put that out front. And then take a look at this right here. Right, and we'll scroll up. Do you see how that is exactly what that is there? All right, but k is 1. So this is actually all of that. Okay, so we're going to get 1/2 times sine of t minus t cosine of t. K was 1. All you gotta do is go back and look at that rule, write it down, and you can see that that's what it ended up being. Right? Then we get plus cosine of t minus sine of t. And that is our answer. You'll have these charts, you'll have these rules. I'll tell you what I will give you on a sheet of paper. That might change semester to semester, but you will get something that will tell you what you will be given on your next test.